All right. Okay, if you're looking at this, I assume it's Monday night. You've had a class already, back in the remote setting. And the hope is this week to introduce the last bit of material for the term and to practice that the whole week. No tests until next week, probably a week from Thursday. Get a chance to get in the classroom and really, probably a week from Friday, get in the class. No, probably going to give you 2 tests. Break it up into 2 parts, 25 questions Thursday, 25 questions Friday, so I can have eyes on the prize. Okay? I do have some concerns of calculator usage in the class, but not going to bring it up because no way for me to prove it. And therefore, I get to watch it. And hopefully, problems that you got right up to this point, I don't see a real drop off in a score. If I do, I'm concerned. All right. And we'll just leave it at that. So if that's you, you got some real work to do. Okay. Let's talk about absolute max and absolute mins. And in this particular problem, we're going to try to find the absolute maximum on a closed interval from 0 to 2. And what a closed interval is that you need to also, well, it's basically a window. So that's a real nice mnemonic device. There's our word of the day, mnemonic memory device. Why is it a memory device? Well, closed, you can kind of get a feel for the brackets here. Closed, right? And so what would be the absolute max of something that looks like this? The absolute max is actually at the endpoint over here. So you've always got to, when a closed interval, you always can immediately throw the endpoints and plug them in. 0 gets you 4, 2 gets you 0. And those are candidates, 4 and 0. Well, 4 is the candidate right now for the absolute max. We got to find out if anything is on the interior of this window, right? Is there something like this, where in the interior, there's a bigger y value? And the way we do that is with calculus, taking derivatives. But before you do, you get a feel for this discipline. Always get a sense of what do you think this thing looks like? What does it look like? So you pause the video and see if you can, without a calculator, see if you can get a feeling for what that looks like. I'll just do it. So I can see that I'm starting on the y-axis at 4, 0x. That means it's flat right there. Concave down and comes back up. So I know I've got some symmetry here by the look of it, and also some mins. Looks like this is going to be over this interval. Well, I don't know. I don't know what this number is yet. So, 2, 0. Yeah, I don't really know. I mean, that could be a height of 0. That could be a height of 0. Could be here. Could be imaginary. We got to go to the calc. All right. So we're going to look for slopes of 0 and where we change from first derivative test, local min. Slopes are going down, then they're 0, then they come, or undefined, could be a cusp, right? So negative to positive gets me min. So I'm looking for when slopes are positive to negative, and probably for the most part 0. And so I'm looking for plus to minus. So I've got to actually dive into the first derivative. Another way to prove that we have max and mins, of course, is concavity. So at these x values, it's the second derivative negative. Concave down, proves max. At the x value, that the critical number that we find is the curve concave up, second derivative greater than 0. So there's 2 ways to prove maxes and mins. And so y prime, 4x cubed minus 10x. Let me just make sure I'm doing that right. Sometimes I'm getting too close to things. So we're going to factor that. We're going to set that to 0. We're going to take a 2x out times 2x squared. That's right, minus 5. Okay, that looks to be okay. Equals big times 0. So we got critical numbers at 0 with a sign change. And we got critical numbers at 2x squared minus 5 equals 0. So 2x squared equals 5. So x squared equals plus or minus root 5 over 2. So the positive is root 5 over 2. We don't care about the negative, but I'm going to put it in so we can get those sign changes. So we can definitely see if we put a huge number in that's positive, negative, positive, negative, and positive, negative. Yeah, and at 0, positive to negative kind of corresponds to, well, I don't know the x-axis, but we did have this kind of shape, right? And yeah, that makes sense. We're going from positive derivative to negative. So that proves that. Now the question is, what is this vet root 5 over 2? Come on. Whole thing's in root 5 over 2. Okay, excuse me. That's not the same thing that I wrote. Big time mistake there, 5 over 2. All right, so the square root of 5 over 2 is 2.5, so 2.5. Square root of 2.5. Let's think about that in terms of size. Well, we know it's bigger than 1, but it's less than 2, because the square root of 4 is 2. So I'm in a number between 1 and 2. So actually 2 is going to be to this side of this curve. And we're looking for absolute max. This is obviously a min, negative to positive, so we can ignore it. And so therefore our absolute max did occur when x was 0, and the absolute max at that value, when x was 0, I erased my table, right? But you can see that a 0 gets us 4. Okay, so that's the discussion we wanted to have. Looks like I lost a little bit of the squeeze theorem over here. You know, when I was proving, we'll go back and do that since the camera was off it. So, you know, to get a feel for the square root of 5 as, you think of square roots that you know. Square root of 1. Okay, well, that's bigger than 1, so we know that's bigger. And I know the square root of 4, which is 8 over 2. That's 2. So this number is between 1 and 2. So I get a minimum. So 2 comma y is bigger than root 5 has comma y. But I'm looking for maximums. So the only critter that we got is 0. 0 gets us 4. Root 5 over 2 gave us a minimum. And 2 gave us 0. So where's the max? Y value of 4. Okay. All right. So that's, I want to do that type of problem at the start of class for the whole week, because on the midterm, I told you, we had trouble with that problem on the midterm, finding, I think, a min. Now we just add the little bit of extra work, as in absolute max or min over a given interval. All right, so next question is going to be, how about some volumes of revolution? We'll do two each night, and hopefully by Friday, they're less troublesome. My experience has been they're troublesome for a couple of weeks for a lot of folks. All right, but as I said before, come final exam time, most classes have pretty decent success. All right, so when doing volumes of revolution, your mantra is top minus bottom, or right minus left. Okay, right minus left when we're doing calculations in terms of y, top minus bottom calculations in terms of x. All right, so let's rotate y equals x squared. The area bounded by y equals x squared and y equals 2. Let's rotate it around the y-axis. Okay, and just the first quadrant area bounded. We'll rotate it around the y-axis. So you pause the video, give it some thought, and if you're dumbfounded, then just follow what I do, and then hopefully that's the first stage of learning, is following. Then you do it yourself, and then you show it to somebody else sometime during the term. Always good to graph these things. So remember, you pause the video anytime you want. I'm just going to keep walking right through it. So it's good to graph these things. There's y equals x squared. There's y equals 2. We've got this area, and we're going to rotate it around this way. And so if we do, that's facing you, and it's a solid. And if you rotate it around, it kind of looks like an upside igloo. And we're going to measure that volume. All right, so how do we do it? Back to a cleaned up picture. All right, I'm not going to do that. Just going to do this. And we're rotating around this way, which means I have stacking radii. Stacking them. And so I wanted to find that radius. And I do know that the change here is in terms of y. Okay, so I got to solve this thing for x alone because that radius is an x distance, but it's going to be based on the height I'm at. Okay, so looks like x is the square root of y. All right, so I'm going to call this thing the square root of y. And my mantra is right minus left. And my left has an x value of 0, so that's my y. No, it's my x distance. Right? Said that the wrong way. So this is the square root of y, right minus left. There's my x's. All right, just the square root of y at this stage. All right, we're going up to y equals 2. We're starting at 0. So we're going to integrate from 0 to 2. I know it's in terms of y. Capturing all of that? Yeah, I am. All right, and what we have is a circular rotation. Circular rotation with a little bit of thickness. A circle with a little bit of thickness. Don't have my coffee, top of my coffee cup. Oh well, we'll get to it as we keep doing them. So I'm hoping you're thinking pi r squared for the circle with a little bit of thickness, but we're expressing y as, our x's, excuse me, as the square root of y. So take pi out each and every time. Your radius is the square root of y. You square it, you're done. There's your pi r squared. From 0 to 2, you're adding up lots of plates. And those plates have a little bit of thickness. And the accuracy is exact. All right, that's that one. All right, now tougher one. In terms of trying to visualize it. We're going to look at, and this will be tough for you for a while. Y equals x cubed. Y equals 4x. We're going to look at that first quadrant bounded area. Well, it's the only area that's bounded. X cubed, 4x. No, it's not the only area bounded, but we're going to look at the first quadrant area bounded, and we're going to rotate it around y equals 8. Y equals 8. All right, so again, pictures are worth 1,000 words. And then you stop the video wherever you want. X cubed, but we're only going to look at first quadrant, 4x. Okay, we're going to find intersecting points, and we're going to rotate it around y equals 8. So let me get rid of that, and let's just do this. Y equals 8. So I'm going to rotate this around. So this is y equals 8. This obviously is x squared, and this is 4x. All right, and we're going to take this, and we're going to wrap it around there. So somewhere, okay. All right, you're going to get this rotation. Again, it's going to be some kind of bowl shape, empty space in the middle. All right, so what do we got? Vertical distances here. Okay, so this dx going from left to right. So where does it intersect? Where does x squared, excuse me, intersect with, was it x cubed I gave you? X cubed, I'm sorry. So x cubed intersect with 4x. These are algebra 1 skills. X cubed minus 4x, 0. So x times x squared minus 4 equals 0. So we have -2 down here. We don't care about that one. We got 0 to 2. All right, so this right here, 2 intersects, comma 8. We don't care about the 8. Oh, we do, because it is. So it actually intersected right there. All right, they intersected there. Oh, that's interesting. All right, that was important to know. All right, so we got to do top minus bottom. And in this case, what's your top function? It's actually 8. Let me give you a bigger picture here. Clean this up a little. Because I know this is hard to see when you first start. Okay, so this is what we got. We got y equals 8. We've got that and that. Okay? And what you want to define in these situations is your big radius and your little radius. Now, my big radius is actually all the way down to the lower function, which is x squared. And so that's 8. That's x squared. So what is my big R? Top minus bottom. 8 minus x squared. This is my little r. So that's my big R. This defines my little r. What is little r? 8 minus 4x. And so what we're going to do is in one integral, we're going to take the bigger disk minus the little disk, but we're going to do it in one integral, just like we do with Riemann sums. We factor things out. I'm not sure I really want to say that. But this was from 0 to 2, I believe. We figured that out before, right? I did this again. It's x cubed, excuse me. X cubed, right? So it looked like a parabola to me from there. So that is my big R. And so I know I got a pi big R squared, which in this case is 8 minus x cubed squared. That's my big R. Pi little r squared was 8 minus 4x. Right? And I want to get a little bit of thickness, dx, from what to what? 2, 0 to 2. Okay? So that's the calculation that goes with that. Did I show everything? Yeah, good. All right, and that's going to take a little while to practice. And if we did that, then we've got the picture here, rotating around, bringing this out, rotating it around, should give us something that looks like that, and swings around and sweeps. And you get these donuts, they're called washers, space in the middle, and what we're finding is the volume of that shape. That's what that does, right? We'll be doing them in class. We'll be doing them for homework. Let's push on, and I'll do one more problem, and then I'll stop the video, and we'll do a couple more arc sine related rates, that sort of thing. But I think I'll break it up into parts here. So if I really, get lost in some algebra or something, just because I get talking and I forget what I'm doing, then I won't have to stop the video and make a new one. All right, so let's see. So let's do a quick and easy problem here. Let's look at, it's not quick and easy for you yet. So let's look at inverses. All right, I'll give you f of x is equal to, how about I give you 5x to the 4th minus 2x. All right, and I'll say that g, we want to find g prime. F and g are inverses. Hard to find this inverse algebraically, but there's a way to find the inverse at an x value of 3. Okay, and as I said before, these are finger counting type problems. Okay, and there's a nice pattern to finding inverses. You switch the x's and the y's, and if you switch the x's and the y's, if we can find the derivative of this, we get a y2 minus y1, x2 minus x1, right? And if we switch the x's and the y's, we get a reciprocal over here, x2 minus x1, subscripts, not those. That should be subscripts, right? 1 and a 2, 2 and a 1, there we go. x2 minus x1 over y2 minus y1. Okay, you get a reciprocal relationship. Okay? So this is the input. This is an input on this side. What's the inverse of an input on the other side? An output. So the first thing you want to do is to set this function to that input value for g. And then you look at it and you say, hey, does 0 work? Does 1 works? Oh, yes, I can see that f of 1 gets me 3. No, that's good. So now I know f of 1 gets me 3. That means over here, g of 3 gets me 1. Well, I can find the derivative at 1. I know f prime of x is equal to 20x to the third minus 2. Okay, so now I can find what f prime of 1 is. F prime of 1 is 20 minus 2 is 18. Oh, then I know what g prime of 3 is. It's 1 over 18. That's what you're trying to learn how to do. And it's kind of a tongue twister problem. And then later, I'll show you the textbook nomenclature that goes with that if I showed it to you now, might send you through the roof. So we might as well learn what this is all about, and then look at the nomenclature. All right. So I'm going to stop the video there, upload this one to the YouTube channel because I'm still denied access on my Canvas. And I guess I'm still out of Kurzman there. I don't know. Figure it out.